All right, welcome. Today we're going to pull back the curtain on something we use every single second, the internet. We talk about it like it's this abstract cloud, but it's not magic. It's a very real, very physical system of smart machines all talking to each other. And we're going to figure out exactly how it works. Let's dive in.
Have you ever really stopped to think about it? You click send on an email, you load up a website, and boom, that information just crossed thousands of miles in a literal blink of an eye. How in the world does it know where to go? With billions of devices out there, how does it not just get lost? Well, that's exactly the mystery we're going to solve.
So, to make this whole thing less abstract, we're going to do something fun. We're going to follow the journey of one single heroic data packet. Think of it as our main character on an epic mission to get from your computer to a server, maybe halfway across the planet. Okay, so our packet's journey begins the moment you make a request. A tiny little packet of data is born, and right away, it has a problem. It looks at its destination address and realizes, whoa, that's not on my street. It can't get there by itself. So, what's its first move? It has to find the exit. It goes to the bouncer of its local network, the device known as the default gateway. This is its only ticket out to the big, wide internet.
And 9 times out of 10, that default gateway is a router. And routers, well, they're really the heroes of this whole story. The best way to think of a router is like a really, really smart traffic cop for data. Its entire job is to look at our packet, figure out where it's going, and then make a split-second decision. What's the absolute best path to send it on next?
But that's the million-dollar question, isn't it? The internet is this massive, sprawling, almost chaotic web of networks. There are literally millions of possible destinations. If the router sends our packet down the wrong road, it could get lost forever or just take ages to get there. It absolutely needs some kind of map, right? Like a GPS for the internet.
And of course, it has one. It's called a routing table. And it's exactly what it sounds like, a map of the internet stored right inside the router's memory. Now, it's not a map of every single computer. That would be impossible. Instead, it's a list of all the networks it knows about and, this is the crucial part, the single best next step or next hop to take to get to each of those networks.
And this isn't some cartoon drawing. This is what a real routing table actually looks like. So let's break it down real quick. You've got the network destination, that's obviously where we're trying to go. Then you have the gateway. Think of that as the address of the very next traffic cop on the route. And finally, the interface, which just tells the router which physical road or port to send the packet out on. It's literally a set of digital turn-by-turn directions. Okay, so having a map is great, but what good is a map if it's out of date? On the internet, roads are closing and new superhighways are being built every single second. So the real question is, how do routers get and maintain this incredibly complex, constantly changing map?
Well, there are basically 2 ways to do it. The first one is called static routing. This is the old-school manual way where a network admin literally types in every single route by hand. You get tons of control, which is nice, but can you imagine trying to do that for the whole internet? No way, it just doesn't scale. That's why we have the second way, dynamic routing. This is the smart way. The routers just talk to each other, automatically sharing updates about the best ways to get everywhere. It's a self-managing system.
So for our little packet's journey across the globe, static routing is a total non-starter. The internet is just way too big, way too dynamic. We have to follow the dynamic path. We're going to see how the network acts like a living, breathing thing, building its own map in real time.
So how exactly do these routers talk to each other? They use special languages called routing protocols. That's really the best way to think about them. They're just different languages, each with its own set of rules and grammar, all for sharing information about the network. They're like thousands of tiny traffic reporters, all gossiping about the best routes, where there's a traffic jam, or where a bridge is out.
And just like we trust some sources of information more than others, routers do too. You can see a few different languages here, OSPF, EIGRP, and so on. That AD column is for administrative distance, which is just a fancy term for a trust score. And here's the key. The lower the number, the more trustworthy the protocol is. So, if a router hears 2 different ways to get to the same place, one from EIGRP and one from OSPF, it's going to look at the scores, and it's going to trust EIGRP more because 90 is lower than 110. Simple as that. And this is what's so incredible about this system. This constant, non-stop conversation is what makes the internet so resilient. Think about it. If a ship's anchor accidentally cuts a massive fiber optic cable on the ocean floor, the internet doesn't just break.
The routers in that area immediately start telling each other, hey, that road is gone, they update their maps, and within moments they start routing our packet and everyone else's around the damage. The network literally heals itself.
Okay, that's awesome for local neighborhoods. A few routers chatting makes sense, but how does that scale up to, well, the entire planet? How do these little local conversations create a comprehensive map of the whole globe?
The secret is to realize that the internet isn't actually one giant single network. It's a network of networks. And these huge individual networks are called autonomous systems, or an AS for short. Think of an AS as a massive kingdom of routers and networks, all controlled by one entity, like your ISP, say Comcast or Verizon, or a huge company like Google or Amazon. This network of networks structure means we actually need two different types of protocols for two different jobs. First, you have interior gateway protocols, or IGPs. These are the languages like OSPF that we talked about. Their job is to handle all the routing inside one of those big autonomous systems, like managing all the local city streets. But to get our packet between these massive networks, say from your ISP's kingdom to Google's kingdom, you need a totally different kind of language, an exterior gateway protocol, or EGP. This is the protocol for the interstate highway system. And when it comes to those highway protocols, those EGPs, there is basically one and only one that matters. It's called BGP, the Border Gateway Protocol. You can think of BGP as the official language of the internet itself. It's the protocol that all of those huge autonomous systems use to talk to each other. It is the glue that holds the entire global internet together.
So BGP is what stitches all these independent networks into a single global internet. It doesn't care about the little residential streets inside of Google's network. It only cares about the best superhighways to get to Google's network. But this introduces a fascinating and kind of scary vulnerability. See, BGP runs on trust. If one big network accidentally or maliciously starts announcing, hey, I'm the best way to get to YouTube, all the other networks might just believe it. That's called a BGP hijack, and it can take huge services offline by redirecting traffic into a black hole. But when it works, this is the final piece of the puzzle that lets our packet travel from literally any point A to any point B on Earth.
So let's quickly recap our packet's incredible journey. Step 1, it leaves its home network through the default gateway. Step 2, that router checks its map, the routing table, to find the next best step. Step 3, that map is constantly being updated by all the routers chatting with each other using interior protocols like OSPF. And finally, Step 4, BGP provides the global highway system that connects all the big networks together, guiding our packet on the final leg of its journey to its destination. And that kind of brings us to a really interesting final thought. We tend to think of the internet as a static place, right? A cloud, a series of tubes, whatever. But after all this, you realize it's not that at all. It's a living, breathing system whose very map is being redrawn millisecond by millisecond by this constant global automated conversation. So it makes you wonder, is the internet really a place? Or is it just a conversation?